Welcome back, everybody. This is our fifth class in JEE mains previous year questions for chapter Moving Charges and Magnetism of class 12th. Before this video, in this series, we have made several videos, I think actually four videos, and all of those videos are available on our YouTube channel's playlist section. We have also started similar series for NEET also. So if some of your friends are preparing for NEET, then you can guide them through that playlist so that they can also have some practice of previous year's questions. With this again, and if you find these videos useful, then do press the like button, share them, and subscribe to our channel. Also, if you want to like to support us financially, you can scan any of these QR codes in front of your screen and donate us with whatever amount you want. Any amount, however small it may be, will be highly appreciated. With this, let's start today's video. We have covered up to question number 37, I think. Yes, 37 in the previous one. And today we will go to 38, start with 38. So here we have an electron gun is placed inside a long solenoid of radius r on its axis. The solenoid has n turns per length and carries a current I. The electron gun shoots an electron along the radius of the solenoid with speed v. If the electron does not hit the surface of the solenoid, maximum possible value for the v. Now, as mentioned already in the question, that it is a solenoid. And for a solenoid, we know that value of field generated by it will be magnetic field generated by it will be nu node n times I, where n is the number of turns per unit length, which is already mentioned that n is the number of turns per unit length. So this is the value of magnetic field, and the value, suppose this is a solenoid. Let me draw it some bigger. Copy, paste, and let's join that. Suppose this is our solenoid. We are just taking this in a, we can say this is a vertical solenoid, and here we have a horizontal solenoid. Now, magnetic field inside a solenoid is always perpendicular to its axis. So, means magnetic field here will be something like this. Magnetic field will either from left to right or right to left, depending upon the orientation of the current or the flow of the current. But magnetic field lines will be something like this, and this is the direction of magnetic field. Now, suppose we are assuming that magnetic field is something like this. Now, it is mentioned that the electron gun shoots an electron along the radius of the solenoid. Now, radius of the solenoid is something like this. This is the radius of the solenoid. Means here electron is shot perpendicular to the direction of the magnetic field. So let's now only draw the circumference, this one side, and we will examine that accordingly. So suppose this is the circumference. This is this area. Let me make it slightly thicker. Here we have this point, suppose O, which is the center of this solenoid, and this is radius. This is radius of the solenoid. Now we have to project an electron here such like that it does not hit any surface of the solenoid, and we have to make the velocity maximum possible. So what we can do, we have to assume some points here. Let us assume that uh, we can say, I can say, sorry, let us assume this is one of the launching point of electron, that we launch electron at this point, suppose at point A, then some random point at B, and then at point O. So depending upon in which direction electron will go, either electron because electron, as electrons enters in the magnetic field, it will start taking curved path. So suppose let's solve for point A. So either it can take path like this, and in this path it will hit the circumference. Why or I can say it will hit the solenoid. Why it will hit the solenoid? Because when in charge particles enter in magnetic field, its radius is given by r is equal to mv by Kelvin. That is the radius. And if we want a charged particle such that it enters into this region and does not touches any of the surface, means that particle is making complete circle here. What does it mean? That particle is making a complete circle here. And whenever a particle enters in the magnetic field, that entry point, suppose if a charged particle enters at a point A, that entry point work as a, we can say, it start working as a point on its circumference. So if it enter at a point A, there will be some center, suppose let's say this is its center. Then if it start rotating around this center, then it will finally hit the solenoid surface. So only possible case that it does not hit the solenoid surface, that its we can say its path should look like this. Let me rub this one first. Either its path should look like this. Let me choose a circle here. From here. Okay, I have to choose different color for this one. So either its path should look like this. This is one of the possible path in case of maximum radius, that a electron enters in the field and start revolving such like this. Or second possible path is this one, that a electron enters and it start rotating like this. So we have two possible options here. First is the yellow one, that electron enters and start revolving in this circle, and in this the radius is maximum, and that is almost equal to radius of the solenoid. And in second case we have uh, that radius of this rotation of electron is half of the radius of this solenoid. So we have to choose out of the yellow one path or the white path. And by default, it looks like the yellow path is the right answer. But it is not. Why? Because when electron enters on the yellow path, then it would mean that particle has started from this point, and radius for this rotation is r. For yellow path, we will have equation that mv by qb, where v is the magnetic field. But as mentioned in the question, that electron gun shoots an electron along the radius of the solenoid. So here we are assuming that electron gun, that gun is at the center. So when it shoots the electron, the electrons initially at the electron is at initially point O. So when it is at point O, it cannot have the radius is equal to r, because if it is now having radius r, then its path will look like something this. As we know that point of ejection, or that this point will act as a point on circumference, and if its radius is r, then its path will look something like this. As its radius is r, it will follow a circular path, and with the radius r, its center will be here. So in this path, it will strike the surface of the solenoid. So the only possible scenario for this electron ejected at point A to move in a circular orbit is to move in a radius of circle r by 2, so that it can complete a circular revolution without touching the surface of this solenoid. And for that, it will be r by 2 is equal to mv by qb. And from this, we know value of b for solenoid is mu node ni. So r by 2 is equal to mv cube mu node ni. Using these values, we get v is equal to q r mu node n I divided by 2m. And let's check the answer. So in divide we have 2m, and here is q mu node n I r. So option B will be the right answer. Moving to the next one. So here we have a long wire. Okay, wait, let me clear one thing in the previous question. That here Here we got radius r by 2 only because the point of projection for electron was at the center of the solenoid. If we can project that electron at we can say one of the nearby surface of the solenoid, in that case we can have radius r for this rotation for this electron, and in that scenario this this expression will be valid, and our answer will become option A. So it depends upon at which point we are projecting the electron. If we are projecting the electron at the center, then maximum radius it can take, it will be r by 2. And if we are projecting it at near the surface, then maximum radius it can take, it is equal to radius of the solenoid. Now going back to the original one, a very long wire A B C D M N D C. So A B D M N D C. So AB is a, we can say, straight part, BD is also a straight part, then this is a circular part of this wire, and then we have up to infinite again straight path. At D, wire forms a circular turn D, M, and D of radius R. A, B, BC parts are tangential to circle, and the magnetic field at the center of the circle. So we have to find out magnetic field at the center. And as per mentioned here, let redraw these wires, because I think they have some part the diagram is not that much clean. So I'm using the black color. This is our AB wire, and this is our CD wire. And between B and there is no wire. So let me clear that. I draw it white color here. Between B and N there is no wire, and now we have a circular path, a circular form of wire, D, M, N, and like that. So what we will do here, we will use two formulas to solve this question. First, magnetic field due to circle or closed ring, that is, we know that is mu node I times 2R. And magnetic field due to a long conductor, long straight conductor, and that is given by mu node I by 4 pi d sine of phi 1 into plus sine of phi 2. So first come to this AB wire, and we have to find magnetic field at this point O. So let's draw this. Here we have this AB wire, and we have a point of our circular center here. Suppose this is our point O. Now we know to find the magnetic field due to long straight conductor, we need to have these two angles, sine phi 1 and sine phi 2. And if we connect these two endpoints to point O, what we will get? We will get the two angles. So this will be the, we can say phi 1. But in case of phi 2, we are not going to get the phi 2 because we don't have phi 2 here, because the conductor is not extending up to the point O. So what we have to do, we have to manually extend it. We will manually extend it like this, and we will join like this. We are manually extending it, and we make it and we join it like this. And now what we do, now we join this point. So now we get two angles. Suppose this is A is already mentioned here. So this is A, this is A, this is B, this is C. So the angle of OA line, the angle of OA line from OC, because all of the angle has to be measured from the OC. The angles in case of straight conductor are always measured from the perpendicular bisector. Here OC will act as a perpendicular bisector for this conductor. So the angle of OA from OC will be known as phi 1, and the angle of OB from OC will be known as phi 2. And in BC part, as conductor is not here, so we will take it as negative phi 2. So now magnetic field due to this AB part, BAB, we can say will be mu node I by 4 pi. This OC is the distance, and OC, oh, actually already we have N point here. I think yes, N is already mentioned here, so we will take it as N. So this ON is equal to radius of this circle, so that will become R. Now coming to sine phi 1. Because this is an infinite conductor, so this phi 1 will be approximately equal to 90 degree. So first we will have sine 90. Now coming to the plus sine of this phi 2, and that will be in negative degrees. So we will take here negative sign. And now coming to this triangle OBN. So now in triangle ONB, we know that value of ON is equal to radius of the circle, and OD, which is also equal to NB. OD is equal to NB. So OD is equal to NB is also equal to radius of the circle. So we have the value of NB, we have the value of ON, and using these two, we can write the tangent of phi 2. tangent of phi 2, as this is the angle, so it will be perpendicular by base, so nb by on, nb by on, r by r, that is 1, or we can say phi 2 is 45 degree. So here we will get sine, negative sine of 45 degree. Now solving this, let's BAB comes out to be mu node I by 4 pi r. Sine 90 is 1 minus sine 45 is 1 by root 2. So this will be the value for AB part. Now going to the BC part, this one, this long conductor, BC conductor. And in this scenario, we can easily see that this OD will act as a bisector, and this will be the phi 1, and here we will have phi 2. So you can say this will act as phi 1 and this will act as phi 2. And similarly here we can again calculate value of phi 1. It will come out to be 45 degree, and phi 2, as this is an infinite conductor, so it will be approximately equal to 90 degree. So B, magnetic field due to BC part, this BC long conductor will be mu node I by 4 pi of r into sine of phi 1, that is 45, plus sine of 90. So here we will have mu node I by 4 pi r 1 by root 2 plus 1. Now let's check the direction of the magnetic field. That what is the direction of magnetic field due to this BC conductor and due to AB conductor. So if we apply the right hand screw rule, as current is going up, so on this side magnetic field will be going into the page. On the left side of conductor AB, magnetic field will be coming out of the page, and on the right side of this conductor magnetic field will be going into the page. So this field is going into the page. Similarly, if we apply right hand screw rule for conductor BC, then on the lower side magnetic field will be going into the page, and on the on its upper side it will be out of page. So this field is going out of page, and from this we can see that both of these fields are opposite to each other. And now we are only left with the circle. In case of circle, the value of magnetic field will be mu node by I by twice of r. This is well known already. And direction of the magnetic field due to circle, using right hand screw rule, you can find out it is out of the page. So here we will have total 3 contribution. Let's write them separately here. So our total field B is due to this AB plus due to this BC and plus due to circle. Now field due to AB is going, this is into page, this is out of page, and this is again out of page, or out of screen we can say if we are viewing it on the screen. Then it means out of the page direction is we normally consider positive direction, because when we plot our axis we plot them like x, y and z, and out of page is we take positive z axis, and into the page we take them as negative z axis. So these two fields will be positive, will be taken as positive, and this field will be taken as negative. So let's add Let's put the values here. First we have AB, that is negative, and its value is this one. So I will directly copy it so that this is AB, and we have to apply a negative sign to it. So negative sign, because it is into the page. Now plus BC, it is same, but only with positive side inside. It is with positive sign inside. So I will paste the same, and it is with positive sign. And now due to circle, we have mu node I by twice of R. So this is the value of total field. Now we can adjust the values. We can take mu node by I into 4 pi comma here. Mu node I 4 pi R common. Here we will have minus 1 plus 1 by root 2. Here we will have plus 1 and plus 1 by root 2 plus mu node I by 2R. These one get cancelled. We get 2 by root 2, that is root 2. So mu node I 4 pi R into root 2 plus mu node I by 2R. Now what we can take? We can take mu node I by R common. Mu node I by R common. We will be left with root 2 by 4 pi and plus half. We can also take this half common, I think, and then we will be left with mu node I by 2R, and here we will have 1 by we can say root 2 by 2 pi plus 1. And even if we take pi common, out of this, then we will have mu node I by 2 pi R. This will give us 1 by root 2, and from here we will get pi. So option A will be the right answer, and direction will be out of the page. Here direction is not mentioned, so we can also mention direction, that will be out of the page. Moving to the next one. Two very long straight and insulated wires are kept at 90-degree angle from each other in the XY plane as shown in the figure. These wires carry equal current of magnitude I, whose direction are shown in the figure. So the net magnetic field at point P. Now this point P is at equal distance from both of the wires, and we assume that both wires are infinite. So in that scenario, suppose this is wire A and this is wire B. So magnetic field due to wire A, as assuming that this is an infinite wire, so it will be mu node I by 2 pi into distance d, and as per right hand screw rule, we can say this field is into the page or in minus k direction. Now doing similar for wire B, as all the variables are same, so value of field will be same. Only what we will have, we have to find the direction, and according to right hand screw rule, as current is moving from left to right, so this field at point P will be out of the page. And as we can see that at point P, both fields are equal in magnitude, just opposite in direction. Means their net result at point P will give us 0. Net resultant will be 0. And we can also draw a line here, that if we draw a line here at this line, any point on this line will have net magnetic field as 0, because fields will cancel each other. The condition is that distance should be equal. Distance from the both of the lines should be equal, and the current flowing in both of the wires is also equal. That is the condition. Now going to the next one. Thin ring of 10 centimeter radius carries uniformly distributed charge. The ring rotates with constant angular speed of 40 omega radian, or 40 pi radian. It is actually, I think it is pi radian per second about its axis perpendicular to the plane. If the magnetic field at the center is this, then the charge carried by the ring is close to. So we have to find out the charge carried by the ring. Now, as omega is 40 pi, let me first make some space. As mentioned that, so first of all, it is mentioned that angular speed is 40 pi radian per second, means omega is 40 pi radian per second. And we know that 2 pi radian is equal to 1 rotation. So we can find out that number of rotation that charge particle is taking here per second. So omega is 2 times the frequency is equal to 40 pi, and we can say frequency is equal to 20, or we can say here that 20 rotation per second charge is taking. And now using this 20 rotation, we can find out the value of current. As we know that suppose that charge is Q, then I, we know that current is equal to delta Q, change in charge by change in time. If we take this time is equal to 1 second, then here delta Q will be the charge flowing in the 1 second time. And assuming we have a Q charge, then it is taking 20 rotation per second. So total charge flowing in 1 second is 20 times the Q, and time we are taking 1 second here. So current comes out to be 20 Q. So we got the value of current, and radius is already mentioned that radius is 10 centimeter or 10 into 10 raised to power minus 2. We have solved this one. Now it is given that magnetic field at the center is 3.8 into 10 raised to power minus 9. So for a ring, value of magnetic field is mu node I by twice of its radius. So it will come out to be value of mu node is 4 pi into 10 raised to power minus 7 divided by twice of radius, that is 10 raised to power minus 1, into current, that is 20 Q, is equal to 3.8 into 10 raised to power minus 9, the given value of the magnetic field at the center. So we can adjust some values here. This will go on 10. This will go on the top, will become 100. So on this side we will have 4 pi into 10 raised to power minus 5, and here we will have 3.8 into 10 raised to power minus 9 into, and we have Q also here, so Q will be equal to 3.8 into 10 raised to power minus 9 divided by 4 of pi into 10 raised to power minus 5. So it can be written as 3.8 by 4 pi into 10 raised to power minus 4, and we can divide it by 4, so it will be 0.9 and 0.95. So 0.95 into 10 raised to power minus 4 by pi, we can write it further like 9.5 into 10 raised to power minus 5 divided by pi. And as we know that pi is 3.14, So this will be approximately equal to, if we divide 9.5 by 3, what we will get? We will get 3.1 something multiplied by 10 raised to power minus 5. And if we now check all the possible answers, then option B matches. If we properly solve, our answer will be 3 into 10 raised to power minus 5. So here we just approximated our answer. So with this, I end this video here. Hopefully, whatever I have covered here till now is helpful and understandable to you. Again, if you have any doubts, suggestions, or something else, you can put them in comment section. I will try to resolve of those. And again, if you like these videos, then do press the like button, share them as much as possible, and subscribe to our channel. Also, if you want to support us financially, then you can scan any of these QR codes in front of your screen and donate us with whatever amount you want. Any help, whatever small it may be, will be highly appreciated. So with this, again, thanks for watching, and we will meet in next video.